Okay, welcome back. So today we shall start a new topic, and that is metal semiconductor junction. Okay, so we have covered many things till now. More recently we have learned about PN junction, and there are many properties, the current flow, the depletion, and so on and so forth. We also had discussed about capacitance voltage profiling of a PN junction, how it breakdown mechanism, and so on. We had also touched very briefly on the working of devices like LED or photodetector using a PN junction as the basis, right. So PN junction forms the basis for most of the things. You will see that in a metal semiconductor junction, the analysis is surprisingly similar to PN junction, okay, except that instead of P, for example, you will have a metal. So the treatment, the analysis, and many of the things are surprisingly similar, although the implications and the applications might be very different. And now before that, we have to also understand why do you actually need to understand a metal semiconductor junction. Okay, so we have to start with that, and you will always try to recall the similarities with PN junction, so that will help you understand it faster. And in metal semiconductor junction will eventually do the same thing, the depletion, the built-in voltage, the field, and or maybe the current. You know, in the PN junction we had current equation, the drift diffusion current. Similarly in metal semiconductor junction also we will have some current. So because only then we can understand how the devices based on these junctions will work, right. So we will come to that today. So let's come to the whiteboard and get started with metal semiconductor junction. So in general, when I say metal semiconductor junction, suppose this is silicon, it can be p type, n type, anything, okay, maybe intrinsic also. Suppose this is silicon. When I put a metal on top of it, okay, suppose I put any metal, say titanium, I can put titanium, or I can put maybe I can put gold, maybe any metal, okay, or maybe I can put a composite metal like a stack. For example, I might put platinum and then gold, right, a stack of that. Matlab, initially I will put platinum, and on top of that I will put gold, right. So and thickness also could be anything, right. So this is a metal semiconductor junction. So I will talk about only one metal here. Let's not talk about two metals. So suppose I put a metal down here, okay, suppose I put platinum or something else. So this interface, this is called the metal semiconductor junction, right. That is a metal semiconductor junction, and a metal semiconductor junction is very important. Now of course the first question is, why is a metal semiconductor junction important? Because whenever you have to measure any device, okay, whenever you want to measure any device, it can be an electrical device like transistor, power amplifier, it can be LED, solar cell, it can be anything. Whenever you want to measure device, you need to put metal contacts. Suppose this is the side view. From the top view it might look like this is silicon. This is one metal stack from the top, okay, this is one metal, say titanium, and this is another metal, say titanium, okay, from the top view, okay. When you measure a device, suppose these are the two pads for maybe a solar cell, maybe transistor, whatever, okay, so a PN junction, whatever, right. So if you put two metal contacts like this, okay, then only you can measure the current. So how do you measure current? You measure the current in a wafer. On this is a wafer, right, this is a semiconductor sample or a wafer. You measure something using a system or a tool called probe station, okay. There will be probe tips. The probe tips will actually come like this. These are the tips with which you probe, okay. These are probe tips, and they will be connected to some electronics, okay, some circuits and all to measure and apply voltage, apply current, and so on. This will be connected to some electronic circuits and all, but there will be two probe tips that will be connected to arm, and those arms are connected to some electronics and other circuits and all, okay. So you have to put down the probe tips. These probe tips are very tiny. This diameter could be few micron, okay. So when you put down the probe tips on these metal pads, then only you measure IV. When I say you are measuring IV, for example, if you remember silicon in a PN junction, we said in the forward bias the IV looks something like that, and in the reverse bias the IV looks like that, if you remember. How do you actually measure this? How do you measure this? You measure this by, if you have a PN junction, for example, suppose this is P side, this is N side, you have put a contact in the P side, you put a contact on the N side, you have to bring down probe tips like this, and only then you measure. You apply voltage, maybe you measure current, and so on, okay. So you need to put metal pads. You need to put metal pads on semiconductor and measure. You don't just take a piece of silicon like this and just put down the probe tips like this, okay. Sometimes you do, but most of the cases you don't do like that, because these probe tips do not make a good contact with silicon. You have to have a metal pad. Only a metal pad or a metal contact will make a good contact like this, and then you put down the probe tips. There are mainly two reasons, or even more reasons, but primarily there are two reasons why you have to put a metal contact like that. Okay, and that's why that is the importance of metal semiconductor junction. We'll come to what are the two reasons here, but there are actually many things. When we talk about metal semiconductor junction, we also have to understand how we measure and stuff like that. For example, a PN junction is not like that. You measure P, you measure, and the top view, it's not like that. This is wrong. Actually, a PN junction would look in a side view. Okay, a side view, a PN junction. If you take a silicon wafer, for example, this is a silicon wafer side view. Okay, silicon wafer, the side view. So there could be a P pocket here, which is p-type doped. This red color is p doped silicon, and the n type is the blue. The blue is the n type silicon. So you might want to put, this is black is the metal. Okay, so I'm putting a metal contact on the p type, and perhaps I put a metal contact on n type, and then I measure. So it's a PN junction here, right? There's a depletion here, this is the depletion, and on. In reality, it looks like that. Okay, you need to put a metal contact to measure. For example, in an LED, you have a p-type gallium nitride. So gallium nitride is the material that is used to make blue LED, by the way. Okay, the blue LED actually is the white LED eventually that you buy from Philips or any other company, right? So it will be P, and then there will be some layer in between, it's called GaN, and then there is an n-type GaN here, right? So you essentially put a contact to the p-type GaN, and you have to make a contact to the n-type GaN also. So what you do is that you etch it down. Okay, like you come to down. So this is your n-type GaN. This is your p-type GaN, this is your n-type GaN. You put another contact here. This is your contact to n-type GaN. This is your contact to p-type GaN. So when you forward bias, this is plus, this is minus, that is forward bias, then the current will flow and the light will come out here, H nu, light will come out, photons will come out. Okay, in reality it looks like that actually. Okay, so what I'm trying to say is that metal contacts are very important. They are quintessential, extremely essential to making a device, to measuring a device, to actually understand, to make any device you need to put metal contact. Okay, even for wire bonding, this is on wafer, but when you package the device and you put it in a chip, or you want to package module or something that you can buy off the shelf, then you have to wire bond the device. Even for wire bonding, you need to put the metal pads on which you will put like a ball, and then you will wire bond out, okay, to make a package. So metal contacts are very important. Okay, and hence we are going to study metal semiconductor contact. Now what are the two reasons that a metal semiconductor contact is very important? Because number one reason is that the metal that you put, okay, will dictate whether your contact, how is your contact. It will determine actually how is your contact. When I say how is your contact, I mean to say how is the contact between the metal and the semiconductor. What is the nature of the behavior of the current that you will measure across the junction. Okay, for example, if I put, for example, an n-type silicon, and I put two metals here of some metal, say maybe titanium or maybe aluminum, okay, and I measure the current voltage characteristics between them, then I might get a curve. This is IV, by the way, this is IV, current voltage I am measuring. I might get a curve like that, which is linear, which follows Ohm's law, right? Ohm's law, as in like the voltage is increasing, the current is increasing linearly. It's a linear contact, it's Ohm's law. Okay, and this type of contact that will make sure that you get this kind of a linear behavior, this kind of a contact here that makes sure that you get this kind of behavior are called ohmic contacts. Ohmic contacts, because when you put those metal, titanium on n-type silicon, you measure the current, you get this linear kind of a IV, for example. Okay, I'm just giving an example. There could be a variety of metals and variety of semiconductor combinations that you might have. But if you put some other metal, maybe platinum, for example, or maybe gold, example, okay, then you may not be able to get that kind of a linear IV. What you might get, you might get something like that. Okay, it's a non-linear IV. Actually, it will very much look like a PN junction sort of a behavior only. It will have a turn on here, and then after some voltage, it will break down here. It will look like a PN junction, but there is no p-type silicon here. It's only n-type silicon, but the choice of metal will dictate this, and this kind of behavior is called Schottky behavior. Okay, Schottky behavior, which is non-linear, and the contact that's just formed is called Schottky contact. So primarily there are two types of contact: ohmic contact that gives you a linear IV, Schottky contact that gives you this kind of a PN junction like a non-linear diode like IV, both on the same material, which is n-type silicon, same dope. It's the choice of metal, please remember that. It's the choice of metal. It's the choice of metal that will dictate whether you get this or whether you get that. I mean this semiconductor has to be slightly doped to something. If it's completely insulating, you will not get a very good ohmic contact, right? For making an ohmic contact, you need to have charge, okay. So it has to be mildly doped, for example, or even highly doped. So a choice of metal will dictate whether you get this kind of behavior or you get this kind of behavior. In some devices, you actually intentionally want this kind of Schottky behavior. In many of the devices, you actually want this kind of linear behavior, okay. So one of the most important reasons why metal semiconductor junction is important is because the choice of the metal will dictate what kind of contact you make, what kind of IV you get, and that will dictate your device performance dramatically. So it is important that you understand how this metal semiconductor junction is formed and what choice of metals will dictate what kind of contact, okay. And the reason why the choice of metals will either form this kind of a nonlinear contact, okay, or this kind of a linear contact is because of the property of metal called work function, because different metals have different work function. If you recall from your 10+2 or high school physics and chemistry, work function is the energy required to knock off an electron from a metal, okay. So different metals have different work function. For example, titanium has a work function of around 4 electron volt. So which means if you apply an energy of 4 electron volt, you are able to knock off an electron from the titanium. For example, nickel has a work function of approximately 5.5. It's a large work function metal. You need to apply much larger energy or larger voltage to actually nickel to knock off an electron, okay. So the work function of different metal is different, and because of this work function of different metal being different, you will actually end up getting different kind of IV. We will see that, okay. So the choice of metal is very important and metal semiconductor junction is very important. So that's why you need to put metal to actually measure the device. You cannot just have a piece of silicon and you put 2 probe tips like that, because these probe tips are mostly made of tungsten. So you will have only one kind of work function of tungsten. So the contact you form will basically, you cannot change the nature of the contact, whether it is ohmic or Schottky, right. So you need to put a pad down, right. You need to put a pad on the top of pad, you bring the probe tips down, okay. And secondly, whenever you have semiconductor, for example, okay, suppose I take a piece of silicon, and I am taking the side view of a silicon wafer. So this is the side view of, say, n-type doped silicon, okay. When I bring down the probe tips to measure, I told you probe tips actually look like this. This is tiny, okay. This is one probe tip and this is one probe tip. If I don't put metal pad, I just bring the probe tips down, then of course when you measure the probe tip here, it accumulates dust and other junk and atmospheric moisture and all the things, okay. So the size of this actually keep changing. It might gather some dust, it might dust off some dust, and so the size of this keeps changing. When the size of this keeps changing, your current also will keep changing every time you measure, right. Because how much current you are measuring depends on the contact area, the size that you are making. So because of dirt going on off and here and there is no control on the size that you are having. It might be 2 micron, suddenly there might be a big dust particle, it might be 5 micron, right. So the current will keep changing every time you measure an IV. Suppose I take a contact and I want to measure, the first time I get an IV like this, the second time the dirt has become more, maybe when you measure, these are microscopic, I mean these are few micron, you cannot see with your eyes the tips, so you have to look at microscope. You saw that there is a junk here or some residues have come here, so next time you measure the the IVs look something like this, maybe next time you measure the IVs look something like this, then you measure, then the IVs look something like this. So the IV will keep changing, the current voltage characteristics will keep changing as you measure again and again, because the area here is not fixed, okay. And besides, there are moisture, there is all kinds of atmospheric stuff that at the surface you will contaminate, and this surface will keep modifying as the atmospheric condition keeps changing. The humidity, the dirt, the flow of the air, everything will keep. These are very sensitive devices. A transistor, a device is very sensitive. So all these will modify the surface here, all this will modify the contact area, okay. It will modify the area at which the probe tip is contacting your surface, and that will keep making the IV look keep changing. There is no consistency. Hence what you do is that you put a metal pad, and this metal pad is deposited. This metal is deposited in reality, okay. This metal is deposited in ultra high vacuum, or you can say high vacuum. It's deposited in high vacuum. So you put in a chamber called E-beam evaporator or sputtering or something. You pump down so that the pressure becomes low in the chamber where you have put the wafer, and the background impurity reduces when the pressure becomes lower. It becomes vacuum, and once it becomes vacuum, you put the metal, you evaporate the metal or sputter the metal. There are methods to do that. Once you put the metal down, what happens is that in vacuum when you deposit this, this interface is very pure. I mean relatively much pure and pristine. There is no atmospheric moisture and junk and other things, because you are pumping down, you are ensuring there is a vacuum in a particular closed chamber. So, when you put that, then the surface becomes very pure, the metal also is very pure. So, when you put the metal there, the first thing is that this interface becomes very pure and controlled, right. There is no junk and impurity, so there is no reason of changing. And when you put a probe tip down here, the area of the dimension of this width and the length in the lateral direction, you know, this is very fixed. The dimension of the metal pad is fixed. Okay, the dimension of the metal pad, is fixed, because you have deposited a fixed metal. So, your IVs will not change, your IV will always be consistent. Okay, it will always be consistent, right. So, these are very important reasons, and of course, when you want to package a device or wire bond a device, then you have to also need a metal pad, because you need to indium wire, you put an indium wire or something else to package it out. So, metal semiconductor contacts are very important, okay, very important, and you might be, you know, still wondering that depending on the metal, I might as well get an IV like this, or I might as well get an IV like this. Okay, it's very possible, it's very routinely achieved by research people in labs. Okay. So, let us come to the semiconductor theory of why this happens. Okay. So, I told you the most important thing is metal semiconductor. There is a work function of metal, there is a work function of semiconductor. The difference of the two is actually the reason why it is there. Okay. So, suppose there is a vacuum level, you know, the energy of the vacuum level, and that is constant everywhere. So, I take metal. When I take metal, there is a Fermi level of the metal. This is called metal Fermi level, EFM. And the vacuum level, when I say vacuum level, it is the energy needed to knock off an electron from the metal to the vacuum, that is the energy, what is the energy required. Okay. So, I am calling that as the energy, that is the vacuum is constant. So, this energy difference between the vacuum level and the Fermi level of the metal is called the work function of metal, phi m, I am calling it. For example, titanium has phi m equal to 4, you know, electron volt, nickel has a phi m of 5.5 electron volt, and so on. Okay. So, different metals will have different phi. Okay. Now, in metals, if you remember, in metals there are no energy gaps, there are no energy band gaps. Okay. There are no energy band gaps, there is no energy band gaps. The highest field level is the Fermi level, and that is it. Okay. There is no gap here, and actually the metal conducts electricity because the electrons that are there at the Fermi level, it is very high density of electron, like an infinite reservoir of electron, right. They can move because this whole thing, actually it is like a partially field. So, they have a lot of empty states here where the electron can move. Okay. There is a lot of empty states, there is no band gap here. Okay. There is no band gap here. So, please keep that in mind. Okay. This is the metal, the highest energy level is the Fermi level only here. Okay. Now, I take a semiconductor. So, suppose I take suppose silicon, I am just giving an example. Okay. Suppose this is silicon, some semiconductor, this is your conduction band, this is your valence band, and suppose the Fermi level is here, it is mildly n-type dope here. So, the Fermi level is here, it is mildly n-type dope, not very heavily n-type dope. You see the Fermi level of the semiconductor is actually at a higher energy level than the Fermi level of the metal. Okay. So, let me do some nomenclatures here. So, this from the vacuum level is constant throughout, my drawing may not be very correct, the vacuum level is constant throughout. So, the vacuum level to the conduction band, this is called electron affinity, this is called phi. Okay. This is the electron affinity of the semiconductor, and your this vacuum level to the Fermi level of the semiconductor is called the work function of the semiconductor, phi s. Remember, the semiconductor work function can be dramatically different if your doping is p type. If your doping is p type, then your Fermi level will be here, and then your work function will be huge. Okay. So, anyways, I am not talking about from p type now, but what I am saying is that depending on the doping, your Fermi level will change, and that will change the work function also. Okay. So, now this is the Fermi level of semiconductor, this is the Fermi level of semiconductor. Okay, it is straight here, it is equilibrium, and this is Fermi level of metal. Now, the moment you join them, suppose you join them, and in equilibrium, you remember, in equilibrium there cannot be any current flowing eventually, and in equilibrium what will happen is that the Fermi level needs to be constant throughout. In equilibrium the Fermi level has to be constant throughout. So, eventually the Fermi level has to be constant throughout, which means this metal Fermi level, okay, this metal Fermi level and this semiconductor Fermi level have to balance, have to become at the same level. So, semiconductor band has to come down slightly, or in other words metal will slightly go up, so that they will balance. Physically what is happening is that electrons from this side, because this is a high energy, will actually be donated or given away to metal. Metal is like an infinite reservoir of receiving or accepting electron. Okay. So, electrons from this side will come to this side because they are at high energy, they will keep coming until the Fermi levels equal, until Fermi level on the metal side becomes equal to Fermi level on the semiconductor side. This is Fermi level on the semiconductor side. So, both have to equalize. Until that point electrons will keep coming here. Now, when electrons keep coming from this side to that side, what leaves behind here is positively charged. When the electrons move from there to there, what does it leave behind? It leaves behind positively charged donor ions. Okay? It leaves behind positively charged donor ions because electrons have come there, right, from some area here, and that when we have only positively charged donor ions and mobile electrons have no longer been there, then we call that as a depletion region. Much like in a silicon, any PN junction, here also you will have a depletion region because metals, because the electrons from the semiconductor have gone to the metal, they have left behind positively charged ions, and they without in the absence of any electron there, that is a depletion region. But of course, there will be a particular width in up to which the depletion will exist. I am calling it WD for example. So, particular width, because then it will, because only to that extent the electrons will keep coming and it will depleted. After that the Fermi level on both sides will be equal. So, how will it look like, right? So, let me draw it again. So, suppose I have a Fermi level of the metal here. Okay. I am not drawing the vacuum level, I am just drawing the Fermi level of the metal here, and there is a Fermi level of the semiconductor here. Of course, there is a conduction band here, there is a valence band here. Okay. I am saying the joining, right. So, the electrons from here will come here and create depletion. So, how it will eventually look is that, so the way to draw it is that you imagine this point to be fixed, this point, the conduction band point here. Okay. Imagine that, you imagine that this point to be fixed here, and now you move the whole thing down. Okay. So, by keeping that fixed point and keeping the Fermi level down. So, what will happen is that eventually the Fermi level, which is the blue color, the Fermi level will have to be equal everywhere. So, this Fermi level has come down here. Okay. The Fermi level has come down here, but away from the junction, okay, far away from the junction, like this side, no, far away from the junction, what will happen is that your semiconductor is not changing. So, conduction band and Fermi level difference has to remain constant because the doping is uniform in the semiconductor eventually. So, the conduction band and Fermi level had a difference of like this, no, EC, EV, the band gap is also same. I mean, this is just like this, you see this. I mean, the EC and EV difference, this difference cannot change away from the junction, only near the junction things will change. So, this looks like that, right. This is actually okay. So, it will come down a little bit. So, this will look like that, right, EV. Now, you remember this point is fixed from the conduction band in a position eventually initially. So, you basically the conduction band will bend up like this, it will come like that, it will come like that. Okay. So, you see the conduction band has bent up because essentially what has happened from here you can see is that the whole thing is basically brought down, you can say, or you can think this is coming up. So, the whole thing is brought down by fixing this point and this point, the conduction band and the valence band point you fix here, and then you move the whole thing down until the Fermi levels align both sides. Okay. Until the Fermi levels align both sides. So, the Fermi level is aligned. So, you see there is some depletion region here, there is a depletion region here which I call WD, this is depletion region that is devoid of electron, and in the depletion region of course, there is a electric field also. Why? Because you can see that there is a slope, there is a slope in the conduction band, there is a slope in the valence band, matlab there is a field there, and after this depletion region the bands are flat, So, there is no field here, there is no field here, no voltage is dropping, no depletion. So, the depletion only exists here, the depletion only exists here. Okay. The field also exists in this region only, beyond that there is no depletion, there is no field, everything is equilibrium, everything is nice and very nice. Okay. Because there is no field in this region, this is a neutral region. Okay. So, depletion has formed here, and this depletion region will have positively charged ions. Why? Because mobile electrons are not there. Why? Because mobile electrons have gone to this side, no, that is why they are not there. So, this is depletion region. If you draw the charge diagram, then basically what has happened is that this is charge diagram, say this is X. So, this is depletion WD. So, up till depletion you will have positively charged ions, and beyond that you have nothing because this part is neutral. number of electrons, number of donors are same. Okay, here it is positive, and this is balanced by a delta, like a sheet of negative charge, that because excess electrons have come here, no. So, at the interface a very thin density of electrons will basically be there, which will make sure that this charge is balanced. Okay, which will make sure that this charge is balanced. Okay. So, this is how the junction looks. Now, let me come to a new figure here. So, how does junction look eventually? I have metal Fermi level, which is the same as the semiconductor Fermi level. Far away from the junction, the conduction band, the valence band, they are the same. I mean, the conduction band and valence band will have the same spacing with respect to Fermi level, right. This spacing will remain same for only at the junction. Only at the junction, this is metal Fermi level, by the way. Okay. Only at the junction, what will happen is that you have things like this. Okay. Okay. It will go like that, it will go like that. Okay. So, the depletion has formed here, WD, and you see how much has the band bent, do you know how much has the band bent actually. So, let me draw it again. Okay. You see the band has bent, okay, the band has bent by exactly this amount. That is called the built-in potential. Just like in a PN junction, this also has a built-in potential, and that built-in potential, that band bending that has happened, if you recall again carefully, I will draw another picture here. Initially before joining, how was it looking like? It was looking like this is metal Fermi level, EFM, this is semiconductor Fermi level, okay. Let me actually draw it again better. Okay. So, let me draw the metal Fermi level here. This is your metal Fermi level, okay. This is your semiconductor Fermi level, okay. And then you have conduction band, you have valence band, Now, if you recall, I told you there is a vacuum level here, and this, if you recall, is the metal work function. This, if you recall, it is the same, okay. The vacuum level is the same. This is the semiconductor work function, and of course, this is your electron affinity. The difference between the vacuum level, EVAC, minus EC is electron affinity, the Fermi level is the work function of the metal semiconductor. So, essentially the Fermi levels will align. So, the distance, the energy distance that the Fermi level has come down is this much, and that basically has bent here, that is basically this, okay. That is the bend that has happened, because once the Fermi level comes down by that amount, Fermi level will be aligned in both sides. And so, you can carefully see that this amount actually is nothing but this whole thing minus this thing. So, essentially phi m metal work function minus the semiconductor work function, that gives you how much the band bending has happened, that gives you the built in potential. Okay. So, that is the first equation or the first formula you will remember in this. So, this built in potential is nothing but equal to metal work function minus semiconductor work function, right. And then this barrier that has formed over here between the metal Fermi level and the tip of the conduction band of the semiconductor here, this is conduction band of the semiconductor, right. This is the valence band of the semiconductor. So, this barrier that has formed is called phi b, you can capital B or small b either way, phi b, and that is called a Schottky barrier, It is called a Schottky barrier, and that is the barrier between the metal Fermi level and the tip of the conduction band here. So, it is like a barrier. So, you see in this across a junction, this is called a Schottky junction now. This whole junction that has formed is called Schottky junction. But reason, and you will get an IV like this, we will come to that, okay. If you draw the IV, you will get a like a IV like this, and the reason is electrons from the metal will have this barrier to go, no. So, it is very difficult when you apply reverse bias on the metal, which is this regime, the electrons will have a very high difficulty of going from metal to this side. So, the current is very low, eventually it has to break down and then it will increase, it will be very low like a PN junction, okay. It is very difficult to overcome this, okay. It is a good barrier. Similarly, the electrons that are when you positive bias the junction, we are talking about this area, then you positive bias this, then electrons will try to come from here to there, and this depletion width also reduces, and the built in voltage also reduces by QVBI minus VA, whatever voltage you are applying, no, that will reduce the barrier just like in a PN junction. So, if this was the original barrier, then at the application of QVA, your barrier will reduce like this, okay. Your barrier will reduce. So, this barrier will reduce, and the depletion width also will reduce. Okay, the depletion width also will reduce, just like in a p-n junction, because you are applying a positive bias here, which means you can say you are applying a negative bias here. So, you are pushing the electrons away, or you can say this positive bias is basically attracting the electrons. So, electrons will come, but because there is a slight barrier here, but this barrier keeps reducing as you are applying more and more positive bias. So, initially there will be small current, then there will be a turn on, like a p-n junction turn on, when the electrons will now able to come largely, and eventually it will increase a lot. Okay. So, that is the turn on voltage of a Schottky diode, and this is the forward turn on current. This is the current in the on current of a Schottky diode, and the reverse side there will be very little current, because from here metals from the electrons from metal to semiconductor will have a lot of difficulty going. So, it will be very low reverse leakage and it will break down. On the forward side, electrons from the semiconductor will come to metal and it will gradually increase like this after a turn on, because as you keep increasing positive bias, your the potential drop that is happening will reduce. In the reverse bias, this potential drop will increase, like in a reverse bias p-n junction. So, even less electron will come. Right? So, basically this is less like a p-n junction, except that on the p side you have a metal here. This is a metal and an n type semiconductor, but you can have similar metal and a p type semiconductor also. Now, if you might ask that if this is the barrier and this is kind of a junction that has formed and this is the IV that I am getting, then how do I get the linear IV like this? Oh, for that you need a different kind of junction. We will come to that. Okay. So, let us wrap up the class here. And we will take up the next in the next class. So, what did we learn here? We introduced what is the necessity of a metal semiconductor junction, the very important practical, from the practical point of view, how to measure a device and why metals contacts are needed. Then we introduced the semiconductor band diagram for metal and semiconductor. Okay, the band diagrams are in equilibrium. We tried to equalize the Fermi level on both sides, and we saw that you can form a Schottky junction, a Schottky barrier, across which electrons find it difficult to travel, and hence the Schottky behavior is a non-linear kind of a contact here that you form. Okay. There are many things associated with a Schottky junction. We will come to that slowly in the next class, and then we will go to how do you form an ohmic contact, or how do you form a contact to p-type semiconductor. This is only n-type, right. So, all these things we will take up subsequently in the next classes. Okay. Thank you for your time.